Great, then welcome to today's Warren lecture. And it's my pleasure to introduce my friend and collaborator, Professor Ming Chen Hsu from Iowa State University. And just a couple of quick facts about on Ming Chen. So Ming Chen was born and raised in Taiwan and holds a master's from Taiwan National University.
National Taiwan University.
Okay.
So
Ming Chen is from Taipei. And then he came for graduate studies. He came to the U.S. First, he went to the University of Texas at Austin, where he graduated with a master's degree from aerospace engineering. And then he went to the University of California, San Diego, where he did his dissertation on fluid structure interaction of wind turbines. And this dissertation won the Chancellor's Dissertation Medal, so that's the best thesis award of the College of Engineering there 2 years ago. And then he made a very good decision because he came as a postdoc again to Texas, and we were office mates at the Institute for Computational Engineering and Sciences. That's where we met. And then two years ago he went to Iowa State as an assistant professor. So with this, again, welcome Ming Chen to the department, and we're looking forward to your talk. Thank you.
Thank you. Thank you very much. All right. Well, hello everyone. I'd like to thank you all for being here to my talk. I'd also like to thank especially Dominic and the organizers for this great opportunity to present our research work at this prestigious event. So today I'm going to talk about something called Immersogeometric analysis. It's a new technology that we have been working on. Started when I was a postdoc at UT Austin, and we continue work on this project, continue work on this concept and ideas at Iowa State. Also working with Dominic here, pushing the idea forward. And then I'm going to show how this idea can be applied to solve a flow over complex geometries and fluid structure interaction of heart valves. And I would like to first mention this work cannot be done without many of important collaborators, our co-advised PhD student David Kamensky at UT Austin, and also especially Dominic. We have been working on a lot of different projects, and throughout the slides you will see many different interesting applications, many interesting topics that we have been working on right now. Also his postdoc Vasco have been building up the collaboration recently. And my PhD advisor Yuri Bazaris from UCSD, who I believe gave a Warren lecture a year ago here. And also John Evans, who was also our lab mates at UT Austin. He's assistant professor at Colorado Boulder, who also gave a Warren lecture 1 semester ago. So it's really interesting to be here. And also my postdoc advisors, Michael Sachs and Tom Hughes. Okay. And I would like to also acknowledge my research group at Iowa State, a group of PhD students and undergrads who works very, very hard on this topic. All right. Okay. So I would like to first talk about the motivation behind this research work, why we put so much effort into this. And in fact, it's really interesting. This is actually, the heart valve analysis was the motivation of why we want to develop a new FSI technology. And actually, we don't need to go to a lot of details, because 2 years ago when I started this topic back at UT Austin, when they bring this up, I just finished my PhD, and I work a lot on boundary-fitted type of fluid structure interaction methodologies, especially for wind turbine application. And then at UT Austin, when I first saw this problem, I thought I can just do an easy job, use whatever I have developed, and apply to this type of application, and that didn't work very well. So I started to look into literatures, and what I realized is University of Minnesota Civil Engineering, Professor Fotis, and also Henrik is doing a lot of methodology development on fluid structure interaction on heart valves. So I believe many of you have been very familiar with this. So basically, the problem of analysis of heart valve is that if you look at this video, you can see the very flexible leaflet is driven by the flow interacting with the surrounding fluids, and the structure flutters a lot. Now, what happens is if you look at the traditional computational fluid structure interaction technology, okay, I would like to just quickly show you this. It looks a little bit different from the video you saw earlier, but I'm going to use this to explain. The left-hand side is the traditional, I would say more traditional way of doing fluid structure interaction. It's a boundary fitted type. What happens is you mesh the surrounding fluid, fit it to the geometry of your structure, and while the structure moves, you move the surrounding mesh along with the structure. Okay. Now this type of methodology can be applied to many applications like wind turbines and things that has large deformation but relatively mild compared with, for example, hard valve. You have very, very large flutter deformations. In that case, you will run into a lot of issues like mesh distortion, or you need to constantly remesh. In this case, it's not impossible. There are several research groups have been doing this. For example, Professor Taifeng Testuya at Rice University. They do a lot of remeshing techniques. They also apply the same method to hard valve analysis. But we want to look at if there are other possibility or maybe a more efficient way of dealing with this type of application, especially like hard valves. So we look into the literature, and one thing pop out is the non-boundary fitted type. Basically, if you look at this video here, you have a structure that is passing through the background fluid. Basically, the background fluid can move, can be stationary, and the structure will move independent with the fluid. And then you use some formulation to enforce the kinematics and traction constraints. So this is another type, which is very, very popular and heavily used for especially hard valve FSI analysis. So that's two major type of computational fluid structure interaction techniques that has been used in the past. So what's the formulation behind the FSI framework? So in fact, before I move forward to the non-boundary fitted FSI, I would like to just quickly talk about the FSI technique we have developed back at UCSD when I was a PhD student. When we developed this FSI technique, we didn't thought about using this for non-boundary fitted type of approach. We would simply want to deal with non-matching interface. So for example, there are fluids, there are structures, but you mesh them independently. So there's going to be a mismatch at the interface between the fluid and the structure. So you need formulation, you need something, you need a mathematical form to enforce the constraint. So how do you do that? And what we do is, well, we have fluids, we have structures, but at the interface, we basically use augmented Lagrangian framework to enforce the constraint. So you have Lagrange multipliers, and you have a penalty. Okay, if you take the variation of that, this is what you will get. You have the variational formulation for the fluids, you have the variational formulation for the structures, augmented with the penalty, with the Lagrange multiplier and the penalty. And you have a formulation for the Lagrange multipliers. Okay. So what can we do with this? If you combine these three equations together, okay, what you will see is this. You will have a fluid problem plus the structural problem, and you can use whatever formulation you like. Okay. In our case, you can use finite element, you can use isogeometric analysis as long as you use variational formulation. But the key is, right at the interface, you have three very interesting terms. You have the first term called consistency, the second term called joint consistency, and then a penalty or stabilization term. What these terms do for you is it's going to weakly enforce the constraint at the fluid structure interface. So what you see is you have weighting functions from the fluid, you have weighting functions from the structures, you have a mismatch. And then this formula will be able to handle that in a very nice mathematical way. Okay. So back then, we used this and applied to the simulation of wind turbines. Okay, the structure is discretized using something called isogeometric analysis. The fluid is actually discretized with finite elements. And also, you can also apply this to just traditional way. If we do some cardiovascular FSI where you don't have very different meshes between the blood flow and also the vessel, then these additional terms, because your weighting function will be the same between the fluid and the structure, basically your discretization will be the same, this additional term will just drop out. So you recover a fully coupled, strong coupling of your fluid and the structure system. You can also apply to many different type of applications. It really depends on the problem you want to solve. All right. So this is just a little bit background on the FSI, on the formulation we derived earlier for this. And I will tell you there's a reason why I show you this, because the non-boundary fitted FSI applied to the hard valve analysis has a very strong link to this research. This is what we realized in the end. Back then, we didn't plan any of this. Okay, so before I move forward, I would like to show several important ingredients that make this research possible. Okay, so in addition to fluid and the structure, before this, I want to talk just quickly something about isogeometric analysis. And since Dominic is here, probably a lot of you already know what isogeometric analysis is. Okay, I think different people will give you very different, maybe a little bit different definition on what that is. And one thing I like about isogeometric analysis is that in your analysis framework, you use exactly the same function to describe your geometry and also to describe your solution space. So for example, right now a lot of geometry modeling is based on computer-aided design. You can use non-uniform rational B-splines, or you can use something called T-splines. Okay. Now typically, how do you do analysis? If you deal with finite element, you know we need to mesh this with triangles or quadrilaterals, or if you have solid elements, tetrahedrals, you need to mesh it. And then you perform finite element analysis. Now if you use exactly the same function from the design, also for the analysis purpose, then you can skip that step. Okay, so Dominic must have mentioned this before, but the one thing I want to focus actually in our research, recent research, is the integration, using this idea to integrate the design and analysis. So I would like to just show you a video. Okay, so basically, using the idea of isogeometric analysis, we can develop a framework that is under a software called Rhino. So what you see here is, let me see if I can stop this video. Okay. So what you see here is we basically pick a computer-aided design tool called Rhino. The reason we pick it is it allows you a lot of flexibility to program plugins. So you can have crazy ideas and then all program under this software. Under this framework to use the function, for example, non-uniform rational B-spline. That is already provided by this. You don't have to write your in-house. You don't need to write your own code for this. Okay. So what you see here is we would like to use this tool to design a wind turbine blade. Okay. So we begin with something called parameter design. Let's go back a little bit. Sorry. So what you see is basically you can let the user to input many parameters. How do you design a wind turbine blade? You come up with some 2D L4 cross sections that could be locally optimized. You align this up, and then you have a surface that is based on all these 2D L4 designs. Now, you may think building this geometry is trivial, but from my own personal experience, it's not at all, because when I started my PhD, it took me forever. I have no background in design. It took me forever to build my first CAD model of my wind turbine blade. So what we decided to do is, why can't we just streamline this? And using the idea of isogeometric analysis, seeing how we can push this forward. So we came up with this parameter design tool. Okay, everything is designed through parameters. The user input parameters. All right. So for example, you just load this data of the L4 cross sections, and then you just click submit, and everything's programmed in the background. And using this rational B-splines, non-uniform rational B-splines, you can loft the turbine blade geometry automatically. Okay, so you no longer need to learn how to loft, how to manipulate points. Then the next step is you can convert this to something called T-spline to do more local control. For example, you can start to, just like what most people do with finite element, you can start to remove elements, or you can locally increase elements. But these functions are all still your design functions, like splines. It's nothing linked to finite elements yet. Okay? And then you can also, in this tool, we can also give isotropic material on the left, isotropic material on the right, and then you can specify different layers of your composite material. Basically you can give very different properties, and then you can lay it up. So everything, again, is through parameters. Okay? Using these parameters, you have the design of the material. Then you can select different zones easily, assign to the composite material you just specified. Okay? Everything is still under one same framework. We didn't switch between different softwares. Okay? Now what's the next step? You want to apply boundary conditions, so you can just select the nodes, apply the, for example, clamp boundary condition. Okay? And then after that, maybe now I need to know what's going on. What's the performance of this design, right? So I can basically load it with some pressure at different location of the turbine blade. So we select 4 different locations, just apply a pressure load. Then because of the idea of isogeometric analysis. Now this is linked to the analysis directly. There's no more meshing step. There's no finite element mesh. We directly analyze based on this design function that we used earlier. Okay, so you can see that after the analysis, you can see how much the turbine blade deforms. Again, there's no switching between different softwares anymore. Everything's under the same framework. Okay, so finally, as an engineer, we want to know a little bit more. Then, of course, you can just post-process the strain to see how your turbine blade performs. You can see where the strain concentration is. Okay, so this is really based on the idea of isogeometric analysis, that we can streamline the design through analysis automatically. Now, what's the value of this? What's the value of this work? By the way, this is joint work with Yuri and also Dominic. We work several months on this, and one key important is the future of this application, because what you can do is you can simply go back to your design space and then change the parameter. For example, in this case, I want to alter my root. I want to change the root a little bit. You can go back, change the parameters, and then you can see easily you can automatically get a different design with a thicker root. You run through the same process. An undergraduate student can do that. Then you get analysis result. Okay, then you can compare with your result with the previous one and see which one is easier. There's no more complex steps in between. Okay, so this is actually also very good for what we want to do in the future, optimization. You can streamline this procedure, go back to this, change your parameters to do parameter optimization on your design. So this is one of the future applications that we like to use. So that's a little bit background about isogeometric analysis applied to this work. And then I just want to quickly talk about the formulation. For FOU Mechanics, we use finite element-based variational formulation. Variational multi-scale stabilized formulation or multi-scale formulation applied to FOU Mechanics. Okay, so this is basically Navier-Stokes with a stabilization term. One important thing is the weakly enforced boundary condition. I will talk about this a little later. This has been, like I said, applied to the wind turbines in my PhD work. We also compare with experimental data. The structural part, we use rotation-free, K-Hav-Love shell. Now, because we have the second derivatives in the change of curvature, so using isogeometric analysis naturally satisfy this continuity requirement. As long as you have high order enough function across the elements, then this will be satisfied automatically. Then we also use like classical laminated plate theory to be able to construct a homogenized composite panel. We apply this to the wind turbine blade design, compare with the real experiment from Sandia, check the frequencies. Also recently, again, working with Dominic, we moved forward to simulate the entire rotor-tower structural interaction. This is all under, everything is modeled as a shell. So the tower is basically steel, thin steel plate, nacelle, and the rotor are composite rotor. And this is loaded by pressure. The rotor was rotating. And the key is this shaft is very difficult to model. And Dominic came up with the idea, say, why don't we just use something like penalty to enforce the constraint between the rotor and tower? Well, that was an easy sentence. That took my student like 6 months to program that, but it worked. So, all right. Okay. All right. So that was the background of what I worked earlier and also currently. But still, there's nothing linked to a non-boundary fitted approach yet. Okay. So starting from this slide, I'm going to show you how this idea is applied to be able to simulate like flow over complex geometry in a more efficient way, and also how to apply this to a very large deformation through structure interaction problem. Okay. The first example we look at is the flow over a sphere. The reason we do this is before we move forward to fluid structure interaction, maybe we should just think about whether we are able to do computational fluid dynamics. Okay, so we took a step back. We just say, okay, there's a very simple flow over a 3D sphere. Some people do flow over 2D cylinder. It's a similar concept. But then we're going to see if we are able to come up with a non-boundary fitted method, non-boundary fitted approach that is able to resolve the flow field. Okay, so basically you have a uniform inflow that is passing over this sphere. A very important thing of our study is that we want to see how accurate our new method. is. Okay, so we look into the literature, how people deal with this problem. And even with very low Reynolds number flow, Reynolds number 100, you can see the flow is mostly steady. When Reynolds number 300, you have periodic steady state. The flow is going to oscillate behind the sphere. Even with this very low Reynolds number, you see a huge range of the, for example, drag coefficient. This is the recirculation length. Or for unsteady flow, you have drag coefficient again. And then you have Strohol number, basically the frequency of the vortex. You can see there's a big range. Okay, so it's very hard to compare with the literature, the numbers from the literature, to see how accurate your method is. What we decided to do is, why don't we just come up with our own reference data, our own boundary fitted approach? Okay, and we have done this for many, many years, so we should be able to do that. So we took the problem, mesh it in the traditional way. So basically, if you have a boundary, you have a structure, your element will need to fit on the surface. You need to fit to the boundary. And of course, you don't mesh the interior. Okay? So the good thing about this is we are going to use exactly the same formulation. We're going to use exactly the same fluids formulation. Okay, there's no ambiguity there. We use tetrahedral elements. We use the same element type, linear tetrahedral elements in this case. And this is the number of mesh. And we first tried to do mesh convergence study. Okay, we tried different level of meshes. We do one level of refinement, do another level of refinement to have a converged number, and that is the target value we will try to, we will see if we can match. Okay, so this is our reference data. So the new method is a little bit different. We no longer need to match, we no longer want to match the mesh to the surface. Okay. Now for this flow over cylinder, now you may wonder, you look at this geometry, it doesn't look very complex. So why am I showing you all these different methods just to solve a flow over sphere problem? I promise you later I will show you a more complex example which requires a lot longer time to mesh. Okay, mesh is one of the most time-consuming, labor-intensive procedure in terms of analysis, design analysis process. Okay. So, but let me show you this first. We basically take the same sphere. Now we no longer match the boundary like what I did before. I basically just mesh it randomly. Okay, the mesh is allowed to just cross the boundary, goes inside. Okay, you can do whatever you like, but of course it is suggested that you do want to cluster your elements towards the boundary. So the boundary does cut through the elements, but you do have some concentration there. Okay, to resolve the boundary layers, of course. If you don't put elements there, then of course you are not able to capture anything. Okay, but the key is you have the freedom to mesh in a way you don't have to match the boundary. So for this non-boundary type approach, there are several issues. Okay, the first question is, now we don't have the degrees of freedom on the structure surface anymore. We don't have the degrees of freedom there anymore in the fluid mesh. So how do we enforce a Dirichlet boundary condition? So for example, no slip boundary condition. I want the velocity on the surface to be 0. How do I enforce that? That is actually the first, almost everybody dealing with immerse type of method, that's the first thing they need to figure out. The traditional immerse boundary approach that you can build a forcing term to try to push the fluids out. In our case, it's actually very interesting. Back then we were still thinking, what should we do with this? What kind of method should I use? We also see something called like immerse finite element method. But then, one day, we look back to our non-matching interface formulation. It is basically a formula that is used to enforce a constraint weakly. So basically, if you have a surface discretization, I can integrate over that to enforce some kind of constraint. Then we said, well, why don't we just match the surface? They don't match, that's fine. But we just integrate over the surface using exactly this weak enforcement of Dirichlet boundary condition formulation, weak BC, and see what happens. And in fact, we have a lot of experience in this. When we deal with the FOU Mechanics problem before, we usually do this weak BC, non-traditional way of imposing boundary condition. For example, if you have a no slip, velocity should be 0. We do not set the velocity to be 0 there. We basically have a weak formulation to weakly enforce this constraint. And what this allows the flow to slip a little bit on the surface. So even though you have a little bit coarse resolution of your boundary layer, you are still able to resolve the flow field in the interior. And of course, you're not able to resolve the boundary layer completely. But then, because of this release of the constraint, you don't have to resolve the boundary layers to be able to get the accurate result. But that was what happened back then. In this case, we just apply directly for this immersed type approach. And this is how we impose the boundary condition. Okay. So that was the first thing. The second thing is a lot of immersed approach is that basically your structure cuts through the elements randomly. Okay, so it's very, very difficult to control the quality of your boundary layer mesh. And one thing about this weakly enforced boundary condition from what we learned earlier, from 2005 to 2012, is that even with larger element in the boundary layer, you're still able to resolve most of the flow quantities accurately. Okay, so that gives us a little bit more flexibility in terms of choosing the element quality near the non-matching interface. Okay, so that was the second thing. Now the third one, which was really, we have to thank Dominic a lot on this, is the integration. So this is one thing we didn't think about back then. So we basically if you look at this 2D problem, you have a cylinder, your flow is going around the cylinder, and you do this you do this immersed mesh, so you have all these meshes inside. Of course, you want to throw the inside away. I don't solve for them. Okay, I don't care what's going on inside. And the weak BC will enforce the boundary condition, no slip condition right at the interface. But for finite element formulation, you need to integrate. Okay? And if you look at the Gauss quadrature integration, you will see that you no longer have a smooth integration anymore because you have these discontinuities. Okay? And back then, I did not believe that this is very important. But Dominic had many years of experience in adaptive quadrature, especially for a fictitious domain method, a finite cell method. Okay? So what he suggested is that why don't we just cut the element into smaller pieces to improve the integration. Okay, it's very important. We only improve the integration. We are not adding any more functions. We are not doing adaptive meshing. It's just simply improve the integration. In other words, our integration is going to respect the geometry. If you look at the original shape, original element, it's that big. And you probably have 9 integration points here, 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 and here, here, here. You have 9 integration points. You try to capture this curve. It's probably not going to be very accurate. Now, if you do adaptive quadrature, you can see your integration rule is going to be better respect your geometry. And why do I keep mentioning this? It's because of the result. The result was very, very, it's really, really important, especially, I believe, for the non-boundary fitted simulation. Okay, and this result is going to show you the accuracy, the importance of the accuracy in terms of geometry resolution. What you see right here is, if you just do the traditional non-boundary fitted or immersed boundary method, you don't really respect the geometry, okay? Well, in certain sense, to some extent. Then you get a drag coefficient like this. If you look at the convergence here, what we do is not putting more resolution. What we do is not adding more functions. What we simply do is we do the integration respecting the geometry, and then you can see it actually converges to the boundary fitted data very, very, very well. Okay. And this greatly tells us that, well, geometry is not something we talk about every day. It's also something linked back to the idea of isogeometric analysis. We want to start to respect geometry in terms of our analysis framework. When we start to respect that, you can see you remove the geometry error and you are able to converge to the boundary fitted solution in a better sense. Okay. Yeah. Drag coefficient? Yes. It's basically the force in the force.
Can you please repeat the question because it's recorded?
All right. Basically, the question is how do we calculate the drag coefficient, yes. Right? So basically, that's the force integrated over the surface, the pressure plus the viscous force integrated over the surface. The force in the string direction, that's the drag coefficient, and the force in the vertical direction will be the lift. And lift should be 0 in this case.
Do you have an analytical solution for drag coefficient?
In this case, Reynolds number 100, I'm not sure. And also for 3D sphere, I don't think there's an analytical solution for Navier-Stokes. There may be for a simplified no, sorry. It may be for like potential flow. You are able to derive the analytical solution. For Navier-Stokes, I'm not aware of there's an analytical solution for this. Yeah. Yeah, it is laminar flow. Yes, it is laminar flow. Yes. Well, at least in the literature we look into, there were no analytical solution that was started for this. All right. So also for Reynolds number a little bit higher, we get a very similar conclusion that with adaptive quadrature we get much better result compared with the boundary fitted case. Okay. But now the important key is we do want to go to turbulence flow, especially we want to apply this for Harvard analysis, right? The Reynolds number is around 4,000, or maybe a little bit higher or a little bit lower. But we want to see that range. In the turbulence regime, are we able to still use this non-boundary fitted approach to capture some important quantities? Okay. Now in this case, this is still an ongoing work, but you can see that the prediction of the solution is a little bit higher than some reference data, but it is actually pretty, I would say it is actually pretty close to the DNS result. And I think we know the problem of this. I think our computational domain is a little bit too narrow. And the computation of this is very expensive. It takes about 2 to 3 weeks just to compute a flow over sphere problem. So it's not easy to collect data like this, but we are working hard on this. But it does show that for this immerse type approach, with adaptive quadrature, okay, sorry. Oh. It does show that we are able to capture the solution, getting closer and closer to the reference data. All right. Now, if you look deeper to what's going on for this flow over sphere problem, and what you see is what we look at is we look at the pressure coefficient, basically just the pressure over the sphere. Okay. So if you look at the pressure data, you can see that our pressure actually matches the DNS result very well. Okay. And from this picture, you can also see again. The adaptive quadrature plays a very important role. You converge the solution. Without the adaptive quadrature, you are a little bit far away, and it does converge to the DNS in a pretty good way. So from this, we know that the pressure is resolved pretty well. So it must be the viscous force, which is usually notorious for a non-boundary fitted type approach. Okay, so that is the direction we are going to look at to improve this non-boundary fitted approach for high Reynolds number flow. All right. So finally, I would like to mention why this non-boundary fitted approach is very important for flow over complex geometry problem. The application we look at is a flow over a real tractor design, and this is mentioned by one of the local company that they mentioned. I was presenting all these ideas of isogeometric analysis, integrating the design and analysis. And he said, well, I honestly don't really care about that, because what happened to us is that to do a CFD analysis, it took us about 3 months to be able to mesh the surrounding flow field of the tractor because of all these detailed features they want to model. Okay, it is so difficult, so challenging to clean up the geometry, then to match the surrounding flow field. And he was asking, is there a better way to be able to skip that step, to save people a lot of time in terms of analysis, in terms of speeding up the design process. Okay. And that was the motivation. That was really the motivation, along with the Harvard analysis, that we want to see what we can improve this non-boundary fitted type approach. And what you see right here is we don't build a boundary fitted mesh anymore to fit the design of this tractor. You can see this tractor has some detailed features, including the mirror, and with very, very small, very thin pipe. You also want to mesh, okay? And I will tell you what's going on if you want to do boundary fitted approach on this. Okay, but this is in general the non-boundary fitted mesh we come up with. Another attractive thing we decided is also we realized this through the interaction with Dominic, that there are many open source free software out there. For example, NetGen or Gmesh. Using these free software tools, we actually used this tool before back in San Diego. We use this tool, try to mesh some complex geometry, for example, just wind turbine blade. It was very challenging, or ship hull. It was very challenging, very time-consuming, and the mesh quality is actually very bad. Because using this tool, we try to match the boundary, and that maybe the constraint is not satisfied very well. We don't really know. We are not meshing expert. We don't know what's going on there. So it didn't give us a very good quality mesh, or the quantity of interest we want to resolve. But for this, for non-boundary fitted approach, the mesh can be generated automatically, scripted through this GMesh tool. You can specify the length scale at different locations. I can say I want to put smaller elements here, larger element there. This can be done very easily. Okay? But it's also much easier to generate a computable mesh. Because you don't have to really satisfy the constraint of fitting the boundary, or fitting this small, this very high curvature or very small kink anymore. You can match this non-matching mesh in any shape you like. Okay? As long as you control the element size. Okay? So this is just an example to show you different mesh generation tool gives you a different type of meshes. So you can see, even though these two are both non-boundary fitted mesh, we use different tools. You can see with very similar mesh quality control, we get a quite different element concentration. So this will still need to be improved through the scripting. But what I want to show you is actually this. This is, again, for this tractor problem, we want to see how well we can resolve the problem. So we want to match our computational data to, our non-boundary fitted data to the boundary fitted mesh. And what I want to show you is, for example, if you look at the small feature right here, okay, just give you an example. If my surface mesh size is 1, I can specify 1 here, then it will be meshed automatically. If I specify 1 here, then typically what you will see is it's not meshable. Because of this small feature, it is not able to resolve. It's not meshable with this length scale. So what happens is you need to manually go in, either clean this up, remove that small feature, or you simply specify a smaller element size. And this is very time consuming. I've been doing boundary fitted simulation for many years, and I know how much time it takes. We don't tell people this, but I know how much time it takes to build a computable mesh for a complex geometry. It's really a pain. So in this case, this scripting, you can really just script it, disregard this small feature if you don't want to know what's going on there. If you want to know what's going on there, of course, you have to mesh it. But maybe I don't. I don't want to know what's going on there. So this can be done very quickly. And also, if you see the boundary fitted mesh, it takes about 1 hour to build this 8 million element mesh. But when we use GMesh, we have a little bit more, about 11 million elements. We only took us about 5 minutes. Okay. Now start to think, if we are doing fluid structure interaction, when this geometry is moving around, you need to constantly do remeshing. This will play a very different role. Okay. All right, so just a quick movie of what the flow field looks like. You can, it's really not that special, but it's just you can see a lot of turbulent flow in the back, and you can see the flow field is actually quite reasonable. Even though this is a non-boundary fitted approach, the flow field understands there's a geometry sitting right here. Okay. And this is the pressure distribution over on the tractor. So overall, the tractor looks okay, but you can zoom into the detail, like you have stairs, you have this pipe, you have this, very small features, and also the mirror. And you can imagine, if you want to mesh everything, using boundary fitted approach, you have to do a lot of labor intensive work. In the non-boundary fitted approach, basically we just ignore them. Okay? So it really depends on what's the quantity you look at. For example, we look at the pressure distribution over this surface. So this is the pressure distribution over the top surface, and this is the pressure distribution over the bottom surface. You can see in most of the places, okay, we match it in a reasonable way. I have to say it's in a reasonable way. It's not perfectly matched, and we don't expect them to perfectly match. And this is Reynolds number almost 3 million. Okay. But sometimes if you look at the smaller features, with some meshing generation tool like NetGen, we are able to capture that. Maybe locally we have smaller elements. But if we have larger elements, we are not resolving these small detail features, then of course you are not able to capture that. So this is what I mean by, if you do want to know what's going on there, you have to pay a very good attention to this. If not, if you just want to look at the overall drag coefficient, you can see that it's actually pretty similar between these two methodologies. And this gives you a lot of flexibility when you want to move forward to, for example, optimization. You want to do this simulation many, many times, or through structure interaction, then this will give you a lot, this non-boundary fitted type approach will save you a lot of time and give you a reasonable answer. Okay. All right, so finally, I just want to use the last maybe 3 to 4 minutes to talk about, okay, still have time. So I just want to use the last few minutes to talk about what originally motivated us to do the non-boundary fitted type approach for the computational modeling. And it was actually a simulation of a bioprosthetic heart valve. Mechanical heart valves are mostly rigid body motions, but for bioprosthetic one, you have very thin, flexible structures. So like the video you saw earlier, it's going to flutter a lot. So what we are going to do is we're going to see what's the methodology can be proposed to solve this. And the first one we consider is exactly the non-matching fluid structure interaction formulation we used earlier for the wind turbine. Because if you look at the formula, you do have a fluid, you do have a structure, you do have these additional terms that was derived originally for the purpose of enforcing constraints at the non-matching interface. And for this non-boundary fitted approach, it is really just a non-matching interface. So why don't we just use these additional terms to enforce the constraint there and see if the fluid structure can be coupled properly, the traction compatibility, the kinematics compatibility can be satisfied through this. Okay. What we found out is for a bluff body, it is okay. It is actually performed very well. But unfortunately, for a heart valve analysis, where the heart valve is a thin structure, thin leaflets, okay, what happens is if you look at the formula, there's an integration of your stress turn over the upper side of the shell and the lower side of the shell. And what happens is because your background fluid has a continuous function across the elements, these nice additional turns are gone. And what you have left is something called penalty. So in fact, this is a penalty method for enforcing constraints between your fluid and structure. And that, of course, doesn't work very well. Okay. In fact, this methodology improves the robustness and accuracy because of the first two terms. That is derived originally from the variational formulation. And that's what brings in the consistency of your solution space. Okay. So what we actually did is we just directly applied this. That was the first step. Why not just try it? We directly applied this to the heart valve analysis. And what we saw is that using a penalty method to open the heart valve is relatively easy. We were very happy about this. Oh, we were able to open the heart valve interacting with the fluid. It looks fantastic. Then during the closing, the pressure is so high such that if you look at the penalty method, basically you are using the penalty turn to approximate the pressure difference between this thin structure. So that if you look at the penalty turn, that means you need to use a very, very high penalty to be able to capture a very high pressure. And because of this, you have a lot of issues. Conditioning issue, accuracy issue, it's not going to work. So one solution will be simply bring back the Lagrange multiplier along with the penalty in the penetration direction to enforce the constraint. Okay, and solving the Lagrange multiplier is always a pain, and that's when you are really happy that you have mathematicians on your team to be able to solve it. And it's actually published already, so you can find a lot more details in this paper. All right? So again, quickly just look at the 2D. It's a flow over 2D beam. It's an idealized heart valve. For boundary fitted approach, this is typically what you will see. You will see a distortion of the elements, and over time, this may not even be computable. Okay, and again, we compare the boundary fitted with our immersogeometric analysis. We can see the under mesh refinement, the solution also converged to the boundary fitted solution pretty well. And so finally, we directly apply this technology to simulate the coupling between a bioprosthetic heart valve with an artery, an aorta. Okay. And in fact, we did two types of simulation. We do model the arterial wall. So the one case, the first case is we have a fixed artery. Okay, so basically just like a fixed tube with the flow driving the motion of the leaflet. The other is we put elasticity on the wall and to see what's the interaction between them. Okay, and in fact this methodology can be really easy to couple the non-boundary fitted approach with a boundary fitted approach for fluid structure interaction. Because if you look at the formula, the formulation doesn't really differentiate whether you have a boundary fitted or non-boundary fitted or immersed formulation. Okay, so just a very typical simulation. You have a pressure boundary condition at the bottom and the top, resistance also at the top, and this leaflet right now is only modeled as a as a hyperelastic material. We use Remaning material, so it's a linear stress-strain relationship. It's not really a biomaterial. That's one thing we are improving right now. But we just want to see what's the effect of the fluid structure interaction. And these are the results. At the left-hand side of the simulation, basically you can see how the leaflet is driven by the blood flow and within a rigid arterial vessel, aorta. So what you will see is this heart valve actually oscillates a lot, which is not realistic at all. And this was the first simulation we performed. It's actually quite reasonable because if you just imagine, in reality, your boundary, this is actually a well-known effect because in general you have a compliance effect that is due to the elasticity of the wall, right? But if you just model this with a portion of the artery, you are not able to really capture. Also, if you don't include the compliance effect, you don't include the elasticity of the wall, and you don't put any compliance boundary condition here, the energy have no other location to go. All the fluid energy is transferred to the elastic energy of the leaflet. So of course it's going to do a lot of vibration, just like this. Okay. So instead of putting a better boundary condition here, that was the idea last year. We said, well, why don't we just simply try elasticity wall? And you can clearly see that we couple this immersed heart valve with a deformable artery. And you can see, if you look at the flow rate, the oscillation is gone. If you look at the structure, you can also see that the structure performs in a more reasonable way. And if you look at the stress, that's going to be, of course, very, very different. All right? And in addition to that, we also just perform a dynamic simulation. Okay, we just drive the leaflets with a pure pressure load. And you can, of course, expect a very symmetric deformation of the leaflets. But you can see that if you consider fluid structure interaction, you're going to get a very different unsymmetric, and even during the opening, it's completely different shape. So we are hoping that using this technology, we can understand more and improve the design, especially for a bioprosthetic heart valve, to improve the performance, to maybe reduce the fatigue, improve the lifespan of these materials. All right, so that's all. Just some quick conclusion. We have developed an immersogeometric method for a CFD and for FSI. We apply this to tractors and also a bioprosthetic heart valve FSI. Hopefully this is going to, the next step is to use this to improve still improve the computational method, of course. Okay, but then also we want to compare with experiments and see if we are able to match the data. And also we also show that including the arterial wall does have a strong effect, or compliance effect to the system, and you can see the deformation of the leaflet performs very differently. So one ongoing work is the material modeling, try to use a better biomaterial model, for example, FOU type model, to have a nonlinear relation between stress and strain, and to have the exponential stiffening under a larger strain. And also in Texas, they have also conducted the experimental work, collected some data of the deformation, and this is also something we want to compare and validate, and hopefully we can contribute something to the field. All right, so thank you very much, and I would like to thank the funding source, ARO, NIH, DOE, for partially support this work, and this computation is done in Texas Advanced Computing Center, and thank you very much.
Thank you. We have now time for questions, and as you know, the presentation is recorded, so if you indicate yourself, come up with the microphone.
immersed geometric means that part of it is isogeometric, right?
Yes,
And
yes.
that was what the structural part of it, right?
Yes. The very originally, when we came up with the idea of immersogeometric, we actually decided to. It's not fully based on isogeometric analysis. The word looks very similar. Tom really likes it.
But the fluid was just finite level.
The fluid is just finite element, but also the immersogeometric means this is an immersed method, but respect geometry. So that's why you see the CFD. There's no isogeometric at all. It's all triangles, tetrahedrals, but we just better integrate. We do a better integration rule, respecting the geometry, and that improves the solution field.
And my second question relates to these wind turbine simulations.
Yeah.
The rotational velocity of the blades was prescribed or was a result of the flow?
Prescribed. Yes.
I have a question on your, actually two questions. Number one is when you do remeshing for the ALE, what software you use to generate the mesh during
For ALE, we don't do remeshing at all. We basically just move the mesh.
Okay.
So what we do is we solve elasticity. It's just a fictitious elasticity problem on the mesh. Okay, so basically, the motion of the structure is the boundary condition for your elasticity.
No,
so the rest of the mesh is going to move based on the linear elasticity.
Yes, but I'm questioning. I'm posing the question about the fluid mesh.
Yeah.
For the vibration of cantilever, where you have a fluid mesh. Can you go back for the slices?
Yes.
I see that you're.
Let me see if there's a better way to do this.
Yeah. So I see the fluid mesh is moving.
Yes, it's moving.
But no remeshing.
No remeshing. Yes.
Oh, okay.
Many people do remeshing, but well, first of all, we don't have that technology. Second, you do need to. It does cost more computing power to be able to remesh and to be able to project the solution. You need to project the solution back and forth if you have different meshes. If you just move in the mesh, you just use arbitrary Lagrangian Lorentz. So you don't project your solution. It's part of the formula.
Okay. So my question is the second question. I know your paper. Okay.
Oh, okay.
But your recent paper. I want to understand for the penalty term beta. Is it predetermined or is it computed during or adjusted or optimal during the computation?
Depends on the for immersed approach, for non-boundary feature approach. Right now it's just prescribed. Yes, we just pick a number.
So you
so
pick a number.
Right now it's empirically decided, and that's one big important direction we have to focus to improve. I mean, we don't want to just empirically find the penalty value. So, but we don't. We have some ideas, but we haven't implemented anything yet.
So, okay. So then.
But for a boundary fitted approach, this is no longer a penalty term. It's a stabilization term. So you can do inverse estimate to find the value of this stabilization parameter. You can find the lower bound, and you can pick a value that to stabilize your formula. So it's no longer. That's why this Nietzsche's method or this non-matching FSI formulation. This is no longer a penalty term. It's part of, once you have the consistency, adjoint consistency, this additional term is like a stabilization to stabilize your formula. And you can decide the stabilization or penalty is a function of viscosity and mesh size. And also a constant that is determined by the polynomial degrees.
Okay.
Mm-hmm.
Then probably one more question, but it's simple. How would that would work with the high Reynolds number flow as a structure that you show? How would it work for this beta term if you just pick a number?
Well, we try many different numbers. Of course, it cannot be too low, right? If it's too low, it's not going to work. If it's too high, then you have conditioning issue. So usually, typically, from our experience, it's within the range of 100 to 1,000.
Okay.
And that usually works.
Okay.
For now.
Thank you.
Yes. But that's a very good question. I mean, penalty value is going to be the key. How to better determine the penalty value, and that could also be some of the reason we are not getting accurate. Some location we are not getting accurate result yet. Especially it's going to depend on how the background element is cut by your non-match interface, by your boundary, immersed boundary. So different cut should have a different penalty value, and that's something we want to do in the future.
Maybe one more question, last question. No one wants to ask? If not, let's thank the speaker again.
Thank you. Thank you very much.
And proceed to the reception.